Hello everyone, welcome to the lecture series on fundamentals of generative AI and large language models. In the previous session we had started with the CNN and then we have seen in detail working mechanism of convolutional layer, which is mainly responsible for extracting the features. In today's session we will explore the remaining components of CNN. We will look into the activation function ReLU, then we will see the pooling layer, flatten layer and the fully connected layer. Then towards the end we will understand how these layers work together in a deep CNN architecture. So far now if you see in the previous session we have understood that why images cannot be passed as an input to a multi-layer perceptron. The problem here is if you take image as a whole and when you convert that input dimension into a single vector, the size is extremely large. Now when the same size when you pass it, it leads to an spatial information is lost or the parameter exploration. All these are the issues that you have seen. But you can ask from convolution layer, we have still not reduced the dimension. In convolution layer it has mainly focused only on extracting the features, but never you have reduced the size. If you use a padding, whatever may be the size of an image, the same size is retained even in the feature map. So what exactly is an issue? Now we have to reduce the dimension of an image, then only we can pass it to an fully connected layers. Now in order to do it, what all the different layers which will help us? So in the previous session we have only seen the convolution layer. Now we will be exploring the remaining layers. In that, first let us look into the activation layer. So the activation layer here what we are using is a ReLU, rectified linear unit. What exactly this activation function is responsible for? It is responsible for all the pixels which are not contributing for model prediction, which does not contribute much. The features which is being extracted from the convolution layer, if at all if there are any negative values, which means those features are not contributing, then ReLU will eliminate those values. So that is the role of ReLU, which is an activation function. Now for example, let us see, this is the output of the convolution layer. So if I say output of convolution layer, we would have taken an input, we have taken kernel is passed through the entire image and then we are getting the feature map. Now whatever is the feature map that we have obtained from the convolution layer, let us assume that the feature map is whatever we are seeing here. Now when this is passed to an ReLU activation function, what is ReLU does? ReLU is it takes the first value, pass it to max of 0, 1. So what is max of 0, 1? Maximum value is 1, so 1 is retained. Now 14 max of 0, 14, it is 14. Then it takes the next number minus 9. So max of 0, minus 9. So maximum between this is 0. So it is 0. Then 4 max of 0, 4, it is 4. So on so forth, it will pass all the values which are being all the values of the feature map is passed to an ReLU activation function. And what we are going to see from this is, you see wherever there are negative values, all those negative values are converted to 0. And all the positive values are retained. So what is the intuition behind this? The intuition is this is the feature map. What is the feature map? It is the extracted features from the convolutional layer. Now all the features that it has extracted from the image, if at all if there are some features which are not at all important, which are negatively contributing, then those features are not important for us. So ReLU activation function will eliminate all such negative values. So this is the intuition behind. But if you see, the feature map is still the same. Whatever is the size, output size of activation function ReLU, we have still not reduced the size of it. But ultimately, when you have to pass it to a fully connected layer, you have to start reducing. ReLU layer will not help in a reduction of dimension. It will only eliminate the features which are not important. Which features are not important? The which are having negative values. So let's take this example. This is the same example of our convolutional layer. There is an input image. That input image is passed to an kernel, and from there we have obtained the feature map. Now when you look into, suppose if an input image is X, now and you have some kernel that you have taken. This kernel has gone through the entire image and we have obtained this feature map. Now if you look into this, what exactly the feature, how it has extracted the features, observe this values very carefully. Can you see the diagonal values here? The diagonal values are very large. Comparing to any other values, the diagonal values are large, which means what feature it has extracted when you have applied one kernel from the input image X, it has extracted this part. This is the feature it has extracted by applying one kernel. Now in this there are so many values which are not at all contributing. So when you apply it to ReLU, so this is the feature map obtained from a convolutional layer. So this, when you pass it to an ReLU activation function, max of 0,77. The maximum between these two is 0.77. Then it will take the next value, max of 0, minus 0.11. The maximum between these two is 0. So we get 0, and so on so forth. When you pass the entire values, the entire feature map, when it is passed to an ReLU activation function, this is the output of ReLU. Now if you observe here, in this input image X, if this kernel is responsible for extracting this feature, now after the output of ReLU, observe this, we have still retained the same. We have nowhere compromised on that feature which has been extracted. We are still having this. Only thing where you do not have any of the contribution from these positions, all that are converted to 0. This is what ReLU does. So in short, the role of a ReLU is, it is an activation function which is going to eliminate all negatives to 0, convert all negatives to 0. Now if you look into, this is an input image. To this input image you have applied this kernel, and this is the feature map that we have obtained, and when you pass it to ReLU activation, this is the feature map that we have obtained. So this particular kernel has extracted this feature. So that is where you can see this entire value is high, and the same values are retained here. So from this we have extracted this part. Now if you apply the same kernel once again, the same kernel when you apply onto this input image, we once again get the same values, we once again get the same feature map, and the same after ReLU we get this. So to extract a different features, you take the same input, but now you use a different kernel. We have seen this in the previous session, right? We are using now a different kernel. This different kernel, when it is passed through this entire image, we are now going to get one more feature map. This one more feature map, when it is passed to an ReLU activation function, we are going to get this feature map, right? And similar way, when we apply one more different kernel, we get one more feature map, and when that is passed to an ReLU, we get one more output. I hope you can able to visualize this. This is what is the working mechanism of ReLU. Now, how does the output looks? You see, this is an input image. When you apply it to the kernel, this particular kernel, focus on this, when you apply onto this kernel and when you pass it to ReLU, we are going to get this output. And if you observe it very carefully, what is the most important? It has retained only that. In the letter 4, what is what this particular kernel has extracted? It has extracted all vertical points. Can you see, this is vertical and here there is some portion and here there is some portion. This is what this particular kernel has extracted, the features. Now, to the same, when you apply a different kernel, you see, now you have applied this kernel. So, what this has extracted? This has focused on extracting the vertical features. So, it has extracted this part. Previously, it has extracted this, it has extracted this portion, and now it has extracted this portion. So, when you combine, is it not, when you combine this portion with this portion, is it not we get something like 4? Something like this we are going to obtain. So, what is ReLU? In short, before we move to the next one, it is going to eliminate all, convert all negatives to 0, right? So, how is that you write in the code? We have seen in order to perform a convolution operation, you require an input which is of size 64, 1. You require number of kernels 32. Here number of kernels that we have taken are only 2, but in general, I mean in real applications, you will be taking a larger number. Here we have taken 32, and the size of each kernel, how it is 3 cross 3, size of such 32 kernels size is 3 cross 3. Now, the output of convolution has to be passed to an activation function. So, the activation equal to ReLU is what is been specified here. So, this is what is ReLU. One important point you need to understand is convolutional layer is responsible for extracting the features. ReLU layer is responsible for converting negatives to 0. But you have nowhere reduced the size. Whatever is the original input size, if padding is applied, the feature map after ReLU is still the same as original input size. We have still not reduced any dimension. So, let us see how we will reduce in a later slides. Now, let us understand how many number of parameters are there when to perform this particular operation. What operation? Convolution operation. Then you have passed it to ReLU. So, to perform this entire, how many number of parameters are there? How many total parameters that are required in performing this particular operation? So, what is that you require? You require an input. Here the input is 32, 32, 3. 3 here is RGB color image that we have considered. Size of the filter that we have considered is 5 cross 5. Now, why it is 5 cross 5? Why not 3 cross 3? It's an hyperparameter, as I said. So, for this particular example, we have considered 5 cross 5. How many such filters we have considered? 6 such filters we have considered. Now, stride doesn't help us with number of parameters. So, any value, it does not affect the parameter count. Padding, whether you apply padding or you don't apply padding, so once again it does not affect, because for original 32 cross 32, if you apply padding, but original input is still 32 cross 32, right? That is the reason padding, even if you do padding or don't do padding, for calculating the number of parameters, it doesn't have an impact. So, what is the formula that is used for calculating this? The formula is FH into FW, that is kernel or filter height and width. Here it is 5 cross 5. Okay. Then number of channels, how many such channels are there? So, number of channels you will get from the input. If you are considering an RGB, number of channels here are 3. If you are considering an grayscale or binary, the number of channels will be 1. So, since it is an RGB, the channel is 3. Plus 1 bias term, and in 2, how many such kernels we are considering? Number of such kernels or filters are 6. So substitute the values in this particular formula, and then when you calculate, we are going to get this. So wherever you come across the calculation, you can just calculate and see if there are any typos. You can feel free to reach out. So here it is 456 parameters. So which means to perform a convolution operation, we are for this particular input size, we are having totally 456 learnable parameters or these many number of parameters are there. So if you have observed what exactly we are learning the values which are there in this and this 5 cross 5. Because as I said in the previous session, this kernel or a filter is a learnable parameter. The values which you are going to use are not a fixed values. Over a period of time in the iterations, the values are going to get updated. How many such values? It is 456 parameters. Similar way, let us take one more example. Here filter width and height is 3 cross 3. So which means you will have 3 cross 3 and number of such channels here are 3 plus 1, and then how many such filters? Number of such filters are 64. So when you do this calculation, we are going to get this output. Right. Similar way, for the next convolution, the number of the filter size is 5 cross 5. Number of such filters what we have considered 64 and plus 1, and input channel is 64, and number of such kernels what we have considered is 128. So when you calculate, we are going to get this. So just see these values and you can correct yourself if there is any typos. So this is how you calculate how many learnable parameters. This is important concept. You should always know how many such learnable parameters are there after every layer, after every operation that is performed. Okay. Now, this is important slide. What exactly is this is, now you have passed an input image. That input image is passed through a convolution layer, and the output of convolution layer is a feature map. Right. That feature map is also called as an output of that convolution layer. Right. Now, what exactly will be the size of the convolution layer, output of convolution layer? When an image passes through a convolution layer, what will be the output size? And the formula is given as I minus f plus 2p divided by s, which is a stride plus 1 into d. Now, what exactly is this? Let us take with an example and then understand. Now, let us assume this is the example where you have an image of size 32, 32, 3. When I say 32, 32, it is a dimension. When I say 3, it is an RGB image. Filter is a 5 cross 5, which means 5 cross 5 filter, and the number of filters are 6. So which means you have an input image which is of size 32, 32, and there are 3 such channels because it is an RGB, 3 such channels, and there are 6 filters of size 5 cross 5. There are 6 such filters. There are 6 such filters. Now, stride that you are considering is 1 and there is no padding that is applied. Now, if this is the case, after you perform, what will be the output size? Now, you know very well that when one kernel is applied on one, you are going to get one feature map. When a second kernel is applied on an input image, you get another feature map. So now, what will be the size at the output? So just substitute the values in this. Here I stands for input, which is 32, 32. F stands for filter, which is 5 cross 5, and 2p stands for whether there is a padding or no padding. So since there is no padding, this entire term becomes 0. Then stride, since a stride is 1, denominator is 1, and then we have depth. D stands for number of such filters. So output channel, which is filter. So look at this. When we calculate, what is that we are going to get? I value is 32, filter F is 5, padding there is no padding, so 0, divided by stride is 1 plus 1. So 32 minus 5 plus 1, we are going to get 28. If you have observed here, there is no padding that is applied. When there is no padding, then obviously the feature map size is going to reduce. That is where input size was 32 cross 32. After you performed, it is 28 cross 28. Now you can ask, what is this D? Now just imagine, when first kernel is applied onto this input image, we get one feature map. When second kernel is applied onto this input image, we get second feature map. Like this, how many such feature maps will be obtained? It definitely depends on how many kernels that we have considered, right? So since here number of kernels that we have considered is 6, the output you will have 6 such 28 cross 28 feature maps. So this is important. Why it is important? Tomorrow when you try to propose your own CNN architecture, or when you come out with the custom CNN architecture, when you are writing an architectural diagram, always we should specify, after we perform one convolution layer, what is the output size. After we perform another convolution layer, what is an output size, so that you are saying for your architecture diagram what is the input passed and how each of the layer is giving you the output. Now if you doesn't want to get into this math, but if you want to understand, then in the hands on you will see something called model.summary. When you give model.summary, after every layer what will be the output, you will be able to visualize that. Now let us take the same input, but where now you are applying padding equal to 2. When I say padding equal to 2, it is for this input image, it is one layer and it is one more layer. That is the meaning of padding. There are 2 layers of padding that is applied, that is what padding equal to 2. So what will be, definitely when you apply padding, always it will retain the size of an original input. Original input size is 32 cross 32. Apply the formula. So 32 and the filter size is 5 and padding is 2p. So 2 into p value is 2, so it is 4. Stride is 1 plus 1. So when you calculate, we get the value 32. Right. Now when you look into this, whatever why we are getting the same output as same size as the input, because padding is has been applied. So this is how you will calculate the size of an convolutional layer, that is the feature map output size. Now you can ask, what if there are some calculations where we are going to get a decimal value? Then it is very simple, go to floor, apply floor, you are going to get the value as an integer value only, you will not get a decimal. Yeah. So next, so far what we have observed is, you have performed a convolution operation, we have seen an ReLU activation function. In both of these two, we have nowhere reduced the dimension of an feature map. Whatever is the original input, if the padding is applied, we are retaining the same feature map. But when you want to apply it to an fully connected, you cannot pass the same, because parameter exploration is going to happen. So definitely we have to reduce the size. Now if you have to reduce the size, what is that operation that you will do, so that now you are going to retain only the most important features which are sufficient to say it is so and so. Okay. Now for example, you take you want to identify some human being, somebody. If you want to identify a person, you don't require the entire features of a person to identify. Some important features are sufficient in order to say that the person name, in order to identify a person. Pooling does that. Pooling now going to reduce the size of an feature map. Now, when it is reducing the size of the feature map, it has to consider some important aspects. Now, let us understand what exactly is a pooling layer. How does the pooling layer works? It requires the output of ReLU activation. Here, this is what is the output of ReLU activation, where all negatives are converted to 0, positives are retained as it is. Now, I cannot pass the same to a fully connected because the size is large. For this particular example, for understanding, we have taken a smaller image, but in a real world you will not have an image of size 7 cross 7 or 8 cross 8. You will not have such a small dimension one. So, this is the output of ReLU activation. How pooling works is, it requires one fixed size window. So, this is the window that we have fixed. Here we have considered it as 2 cross 2. Now, once this fixed size is considered, now you have to perform an summary operation. What is summary operation here is, now in this window, how many values we are seeing? We are seeing totally 4 values. What are those? 0.77, 0, 0 and 1. Now, the summary operation is whether you want to consider the highest value, or whether you want to consider the lowest value, or whether you want to consider the average of all. So, that is what is the summary operation. First, fix a window, that fixed size window. Here in this example we are considering 2 cross 2, and this window will slide over the entire feature map. Okay. Then we have a summary operation. What the summary operation is, once you fix the window in that particular slot, you apply an operation called a max pooling, or you can apply an average pooling. We can also consider min pooling. I will tell you that. Now, for example, if you apply max pooling, you are going to get the value 1. Then you are going to stride it, and then you perform remaining. That you will see in the next slide. So, by doing this, is it not you are going to get one output, you are going to get this output, and if you see, the dimension has definitely reduced. From this size you have reduced it to 4 cross 4. So, by doing this, what exactly we have achieved? We have done the downsampling. Therefore, pooling in CNN is a downsampling technique, and what it is going to do, it is going to reduce the dimension, spatial dimension, that is width and height of what? Of this feature map. And why is that we are doing this? Definitely it will reduce the computational cost, and that is what is required to pass it to a fully connected layer. So, from this you are only understanding what is a pooling. It is a downsampling technique. How it works? It requires a fixed size window which will slide over the entire, and when a window is on a particular part of a feature map, you will apply a summary operation. Those summary operations can be any one of these. For example, let us understand types of pooling here. Let us take an example where the feature map size is 4 cross 4. Now, you have taken a window size as 2 cross 2. So, window size as 2 cross 2, which means you will take this particular window. Right. Now, when you take max pooling, what is a max pooling? When a window is placed on the onto this feature map, whatever the portion that we are visualizing, in that what is the maximum value? So, the maximum value is 71. So, 71. What is the meaning of this is, the intuition behind is, the most important feature is present here. That 71 carries the most important feature. Yes. Then you have to stride it. So, here the stride will be whatever is the window size by default. Otherwise, explicitly we can specify the stride also. If we do not specify, whatever is the size of the window, that will be the stride value. Since window size is 2 cross 2, stride value is 2, which means you will now 2, you will leave these 2, and this is the next window size. And the max pooling, maximum among this entire is 6, so 6 value. Then again stride is 2. So, you will leave these 2, and then you will come to this portion. So, maximum is 60. Then again 2 you will leave under this portion. So here maximum is 13. So this is what is pooling, where you take a fixed window that will stride over the entire. When a window is placed, it is going to perform a summary operation. Second is average pooling. What is average pooling? It is 71 plus 8 plus 1 is and plus 0 is totally 80. 80 divided by 4. Why 4? Because 4 such values we are considering. 80 divided by 4 is 20. Similar way, you will add all these 4 values and you will divide it with 4, you get this. You will add all these 4 values, divide it with 4, you get this. Similar way with this. What is the difference between average pooling and max pooling is, in max pooling, you are going to take the maximum value. In average pooling, you are considering the maximum, the important feature, that is a max value, and you are also considering the minimum value. And then you will take the average of it. So you get this average pooling. Then we have a minimum pooling. You are focusing only on the least important features. So the minimum value here is 0, 2, here 20, and here it is 3. This is a minimum value. Recently I have come across one more pooling, which is max average min pooling. How this pooling works is, look into this. This is the mathematical explanation for max average min pooling. How you are doing? We will first calculate what is max minus minimum. So now let's go back and then understand what is maximum in this entire value. Maximum value is 71, and what is the minimum value? Minimum value is 0. So max minus minimum is 71, and if that value is greater than average, what is average here? It is okay, let's go back. Average is 20. So 20. How do we get average? Add all the values divided by 4. Which values? Only that window size values. So here 71 is definitely greater than average. Then if that is the case, what is the output? Output is max minus minimum, which is 71. Then let us consider, suppose if this value, if this condition does not satisfy, if max minus minimum is less than or equal to average, then what value you are going to consider is max plus average divided by 2. So this is max average minimum pooling. This is one more pooling which you can look into when you are doing an implementation. So these are 4 different, and if you understand the intuition, when the difference max minus minimum, when this difference is a maximum, and when the difference between maximum and minimum value is large, that means when this difference value is very large, which is 71 in our case in the first example, which means that is the window which has a strong features, or there is a sharp change there. So in that case, we need to retain that sharp information. How do you retain? You will retain that value. Suppose if a max minus minimum is very less or moderate, which means the information, the window is more uniform. In that case, what is required to you is, you require this information, max plus average by 2. You are going to have this information. So this is one of the pooling which I have come across in one of the research paper. So I thought we can discuss that here. So max average minimum pooling. Then let's go back to the same example where we had stopped. So we have a convolution layer which has extracted the features, that is passed to a ReLU, and then this is the output of a ReLU activation function. Now for this you are applying a pooling, and we know that pooling will always reduce the dimension of an image. Now let us see how it is going to reduce it. What is the size of this particular? It is a 7 cross 7. 7 cross 7. So this is 7 cross 7 feature map that is applied to a max pooling. For max pooling, you require a window size as a fixed window size. It's an hyperparameter. Here in this example, we have taken 2 cross 2. And the stride, if you doesn't specify anything, the stride is 2. So now when you perform, here we are applying a max pooling. So among this entire, the max value is 1, so 1. So since the stride is 2, we are leaving the first 2 and then take the next window. So here the maximum, you are applying it to max pooling. Maximum is 0.33. Again you leave 2 and then stride, which will be this value. Again you will take the maximum, which is 0.55. Now leaving 2 when you take stride. So here you just have only 2 values, remaining will be 0, 0. So among this, the maximum value is 0.33. Now stride when you take, you leave the first 2 rows and you will now consider this part of an feature map. Maximum is so on so forth, you will get this value. Now you can ask the question, by doing a downsampling, is it that we have lost some information? The answer is no. Observe this very carefully. When you look into the diagonal, this is what is the diagonal values, which is the original input x, which has extracted this part. Now after you apply the max pooling, can you observe this diagonal? You still have that. So by reducing the dimension, the most important features are still retained. We are not compromising on, just by reducing the dimension, we are not compromising on the important features that it has extracted. Those important features are retained. So this is what is max pooling. So how do you write when you are doing an hands-on implementation? When you want to implement this, what is that max pooling 2D? We are implementing it in Keras. In Keras, you have a function called max pooling 2D. Why max pooling? Because we want to perform max pooling. Now, in this, the compulsory parameter is you have to fix the window size. That pool underscore size, window size is 2 cross 2. When you write 2 cross 2, by default, the stride here is 2. Default. Otherwise, you can explicitly specify as well. When we are doing a mathematical, when you are implementing it, see how we are going to implement it. First, you require an conv 2D because you have to perform a convolution operation. You require an input, which is 28, 28, 1. You require an ReLU activation function. We require padding equal to same, which means we are applying a padding. Now, and we have considered 32 such filters and then 3 cross 3 size of a filter. So once you do this, you are going to get an output, and the output will be once again 28 cross 28. But what will be the, how many such kernels, what will be the depth here? The depth will be number of such filters. Number of such filters here are 32. So this will be the output after we perform the first line. When you pass it to max pooling, so this is 28 cross 28. So pooling, you are taking a window size as 2 cross 2, and stride, if you don't specify, by default it is 2. So when you perform a max pooling, you are going to reduce the size to 14 cross 14. Why? It is 2. So definitely it will downsample exactly by half, and you will not reduce this because 32 such feature maps has reduced to a size 14 cross 14, which means this 32 will be retained as it is. Right. So padding equal to same. Why? Because in convolution you have applied padding. So even in max pooling you will be applying padding. That is the reason why when you don't had values there, it is 0, 0. So this is the this is how you will write in a programming way the operation. Since these two are the functions which are part of Keras, so you will first implement you will import Keras from TensorFlow, and you are building a models, and that model you are going to build a sequential model, one after the other. You are going to place a layer. So you will import sequential from where? From Keras, from TensorFlow.keras.models. Then you have to import these two standard functions, standard methods. So you will import conv2d and max2d. These are the layers. So from tensorflow.keras.layers you will import these two. However, towards the end of this particular week you will see all these in the hands-on. So I hope pooling is clear. So stride will be by default the window size. If you want, you can explicitly specify the stride, then you have to write it in the program stride equal to 1 cross 1. If you don't specify, it will take window size. If you want to change it, you can write explicitly. So this is what is the pooling layer. Now let us understand how do you calculate the output size. Now here how do we calculate this size, what will be the feature map size after the pooling layer. So after the pooling layer, the formula is this, it is nh minus f by s plus 1, this is height, width into depth, number of filters that are used in the convolution layer. Let us directly take this with an example. Suppose if an input image is 5 cross 5 and here the channel is 1, which means the depth here is 1. And number of such filters what we are considering here are 3 and the stride here is 1. So just substitute the values. I'm using it for the height, same thing into it will be for the width. So it is input, so nh minus f, so it is 5 minus 3. So divided by 1 plus 1. So we are getting an output as 3 and this is height is 3, width is 3. So this is what, and into depth here is, since the number of such filters you have considered as 1, so depth here is 1. I hope this is clear to you. So this is what is the so 5 cross 5, this is 5 cross 5. Filters are 3 such filters, stride is 1. So what will be the what is the output that you have obtained? The output that we have obtained is 3 cross 3. And don't consider this is one output, this is second, third, 4, 5. No, absolutely no. You have taken the window and you are moving the window throughout the program. So finally it is only one 3 cross 3 into 1. This is what is the pooling layer. I hope this is clear. So this is important concept where we are summarizing the entire. You have taken an input image. For that input image you have passed to an convolution, ReLU and pooling, and you have taken 3 kernels. So how many feature maps we have to obtain? 3. So those are these 3 feature maps, and I hope you have understood this. This kernel is passed through the image, you get this feature map. Second kernel is passed to the image, and second kernel is you are passing it to the entire image. The kernel is going through the entire image and you get the second feature map. Similar way the third feature map. To do this, how are we writing a code? Input size here is 7 cross 7 cross 1 and then padding equal to same. That is the reason you are seeing that there is a padding layer that is applied. ReLU activation 3 cross 3 filter and 3 such filters have been applied. And after for this pooling, this is the line of code. Now you can ask, can we repeat this entire process? Why we have to repeat it? What if you want to perform once again convolution ReLU pooling? Is it possible? Answer is yes, you can definitely do one more. I'll tell you why to do one more in the upcoming slides. So let us assume now you are again performing one more convolution ReLU and pooling layer, and you have used 3 kernels. What will be the output now? So this kernel will be applied onto this entire 3 matrix. We get one feature map. The second kernel onto this entire you get one more. Third kernel onto this we get one more feature map. So since there are 3 kernels, so definitely you will have the 3 feature maps. But definitely the size will be reduced. Why size will be reduced? Because now the input is not 7 cross 7. The input is these matrix. This is what you are passing as an input to the next set of operation. So this is the feature map that we will obtain. we obtain this feature map. Now you can ask the question why to do this. So let us, I hope this is clear to you. You have taken an input image, 3 kernels, you have passed it to entire convolution, we got these feature maps. Again we are performing another set. So we are again taking the kernels. So for the second convolution, you see the way that we are writing. We are now applying the conv 2D. For this we are taking 3 kernels and each kernel of size 3 cross 3. Since it is a sequential model, no need to write explicitly the input. Definitely the previous output will be the input because we are building a sequential model. That is the reason for second time conv 2D we are nowhere passing anything about the input. Then ReLU is written here and then the pooling is being specified. We get this output. Now let us understand why to do that. Before that we will see this topic called flatten layer. What is a flatten here? Ultimately what is that we require? Now there is an image, you have extracted the features, negative values are converted to 0, most important features you have retained by doing pooling. So but we have still not classified anything. The image, whatever the features that you have extracted, what is that image? Whether it's a cat, dog, what exactly is that image? Nowhere we have classified still. For classification, you have to pass it to fully connected layer. Now go back from our previous session. In order to pass it to a fully connected layer, our image, so far our data is in the matrix form. Right, it is in a 2-dimensional matrix form. Now that has to be converted into a single vector. Why it has to be converted? Because multi-layer perceptron expects the data in a single vector. So therefore, what exactly is the flatten layer doing? Whatever is the output. So this is the output. Whatever is the output that we have obtained after pooling a layer, whether you do 1 pooling, 2 pooling, multiple poolings, whatever, the output of pooling a layer. So that will be in the form of a matrix. So that matrix now should be converted into a single vector. How is that you do that into a single vector? Can you see this? We have a feature map. This feature map which is in the matrix form is converted into a single vector. How is that you are doing? So it is 3 1 1 3 1 1 2 5 0 2 5 0, then 1 4 2 1 4 2. So you are converting it into a flatten and then you can pass it. So what if you have multiple such feature maps? Here there is only one feature map you have converted. When you have multiple such feature maps, you can do this. This will lead to one flatten, this is flatten and this is flatten. So how do you perform this operation? You perform this just by calling a flatten function. Why do we require this? Because ultimately our aim of using CNN is either classification, or you can do a segmentation, or you can do an object detection. Here what we are doing is the classification. If you are using a classification, you have extracted the features, you have reduced the dimension, but you have still not classified what exactly it is. To do that, you have to pass it to fully connected layer. To pass it to fully connected layer, that requires a data in one dimension, in one vector form. To get that in one vector form, the feature maps which are in matrix are converted into a single vector. That is a flatten. That is what it is doing. Now let us try to understand why did we repeated it once again. Now let us assume this entire portion is not there. We have taken an input image, we have passed it to convolution ReLU pooling, and then we have obtained this output. This is our feature maps, right? Feature maps. Now let us assume after this we are passing it to a fully connected layer. If you have to convert this into a single vector, can you see what is the dimension? Here it is 4 cross 4, which is 16. Here you have a 16, here we have a 16, which which means 48 are the features that we are passing to an fully connected, 48. Here this is a very simple example which is of 7 cross 7. But can you imagine this for a real world application where your image size is of 256 cross 256, and after you perform one set of convolution, what will be the dimension? So then if you pass it, then you convert that into a single vector, again is it not a larger value? I hope you are getting this right. So you cannot directly pass such a huge dimension into an flattened layer, convert that into flattened layer and pass it to fully connected. So therefore, this feature map size is still large. In order to reduce that, we are again passing to an next set of convolution. By doing this, we have got a less dimension feature map. Now, what is this size? 4. This is a 4, this is a 4. So is it not just 12 features that you are passing it to an fully connected? I hope you are getting this. So that is the reason why we have repeated it once again. Now from a smaller 7 cross 7 for 3 such kernels, 3 cross 3 size, we have got 48. Again performing, you have got 12. So with this, can you imagine if the dimension is 256 cross 256, how many such times you should repeat so that the final feature map size will be smaller, so that you can pass it to an fully connected? I think you should be able to get that intuition now, right? So once you convert that into an flattened layer, the next is your fully connected layer. So this is your multi-layer perceptron. So you can have any number of hidden layers, you can have any number of neurons in the hidden layer, and the last layer depends on how many number of classes we have. If you are doing a binary classification, at the output layer you will just have one neuron. If you have a multi-class classification, number of classes is what will be there in the output layer. If you are doing a 3 class classification, you will have 3 neurons at an output layer. It's a classification problem. So either it is a binary or it is a multi-class. So how is that? You will be writing a code. You will first call a flatten layer so that the feature maps which are in matrix form will be converted into a single vector. Then 128 is the first, it is an hidden layer which is having 128 neurons. Activation function used is ReLU. Then I am not writing the code for this diagram. It is the code that is mentioned here is a general one. Then since there are 3 neurons here at an output, there is 3, and the activation function that we are using is softmax. From our previous activation session, you must be knowing if it is a binary classification, number of neurons you will write here as 1, and the activation you will use a sigmoid. Because if it is a 3 class problem, number of neurons will be number of classes and the activation function is softmax. After that, you will compile the code. To compile the code, you will be using an optimizer and you will be using a loss function, and what is the metric that you are calculating? It's an accuracy. However, this you will see in the hands-on. The whole intention of the last 2 sessions, that is the previous session and this session, is to give you the overview of how CNN works. So we have a convolution layer responsible for extracting the features. We have an activation function responsible for removing all negatives to 0. Then we have a pooling layer which is used to downsample it, and then we have a flatten layer which is used to convert the feature maps into a single vector and then pass it to a fully connected layer. So with this, we have come to an end of this particular session, and we have come to an end of theory session of week 1. In the next 2 sessions, you will be seeing an hands-on on this CNN. Thank you.